Hi, my name is Mehrnoush Askarpour and I'm going to present our paper that, as its title suggests, discusses a co-simulation approach that combines formal verification of systems modeled by temporal logic with 3D simulation in order to analyze industrial human-robot collaboration scenarios. On the front page, you could see the contacts of my co-authors Matteo Rossi and Omer Triakiller, and also mine, so please do not hesitate to contact us if you have any questions or further interests on this topic. Let us start with a little bit of a background. Traditionally, robotic systems in manufacturing settings used to work in fenced areas apart from human operators, and thus benefiting from both human flexibility and machine productivity was quite challenging. Human operators were only allowed to enter the workspace of robots when they were completely idle. Nowadays, though, robots have changed in size and functionality so that they are capable of collaboration and close interaction with human operators. This helps the combination of human flexibility and machine productivity, but obviously introduces new safety concerns due to close vicinity and frequent contacts between human and robot. Like many other safety critical systems, HRC applications need to go through a rigorous safety assessment prior to mass use, but there are several challenges, such as human non-determinism, dynamic environment, and runtime changes of the workflow. In order to tackle these issues and identify all the possible hazards, we have proposed a methodology that uses modeling and formal verification. Full version of this methodology has been published in a different work, and here I just give a very general overview of it. This approach provides a template formal model of HRC systems with several modules, of which some could be used as is and some others shall be customized for each scenario by the safety engineering team, with providing a few parameters and values to be assigned within the model. The safety engineers provide details needed to model the layout and the executing task, and choose from a library the model of the robot they are using, and then define a desired safety property. The rest, which are human model, definition of hazards based on ISO 10218, which is called Robots and Robotic Devices Safety Requirements for Industrial Robots, and the risk estimation procedure based on ISO 14121, which is called Safety of Machinery Risk Assessment, are ready to be used as they are. The model is discrete, meaning that the layout is divided into locations and human and robot physical shape is formulated by a set of points of interest. When the verification is launched, the model checker exhaustively explores all the possible traces of the model to detect any trace that violates the desired property. If it doesn't find one, safety engineers could be certain that their defined property is always satisfied unless the model changes. Otherwise, if the model checker finds any trace that violates the property, such trace would be reported to the safety engineers to realize the problem, refine the model, and go through the verification again. In order to improve the last step, which is reporting the state of the model with respect to the desired property to the safety team, to better reflect on the hazardous situation and define suitable risk mitigations for them, we want to integrate the results of formal verification with a 3D simulator. It helps the safety team to detect each hazard, its causes, and check the effectiveness of a newly added risk mitigation. Now let's see what are the underlying means of our toolchain. The formal model itself was created by temporal logic, in particular by TRIO, which is capable of expressing the evolution of a phenomenon over time and features a quantitative notion of time. It has temporal operators that relate the current time to another time instant. As for the model checker, we use ZOT, which is a bounded satisfiability checker that as input receives temporal logic models and implements several techniques for checking the satisfiability of those models in an automated manner. Now, the question is which 3D simulator to use. We first collected a set of criteria which was important for the simulator we chose to fit the rest of the toolchain. The first one is capability to model human observable behavior such as move, peek, place, and etc. Several simulators have human agents, but a certain behavior could not be imposed on that agent because they are sort of passive objects in the simulation environment or they follow a random pattern of behavior. So you cannot exactly simulate behavior such as human picks a workpiece from position X and places it in position Y, which is most frequently what we need to do in collaborative applications. Other important factor is for the simulator to set up easily on different platforms for an easy user experience. Then we wanted the simulator to support industry standard protocols and communication methods known for robotic applications such as ROS, YARP, or Collada. Moreover, as we want our tool to be publicly accessible, we look for simulators which are free to use or basically open source. And finally, we were looking for a simulator which is already firmly established and has a large and vibrant community of users. We considered several tools and made a comparison, which is explained in the paper. We don't go through all the details here. But we concluded that Gazebo, Coppelia Sim, also known as VREP, and Morse have the bigger community and more reliable documentation and have the capability to model human agent. We found works proving that Morse performs better for larger test cases with multiple robot agents compared to Gazebo and is more HRC specific compared to VREP. So we decided to proceed with Morse, which is an open source 3D simulator compatible with ROS, YARP, and Pocalypse, has a solid and programmable human agent, and has an easy to use Python API. And this is why we think it is a good fit for our toolchain. We implemented an orchestrator using Python API of Morse that works as a middleware between Zot and Morse simulator. It grabs the output information of Zot, which is technically a collection of predicates and Boolean assignments of logic formulae, and translates them to standard commands that are recognizable for Morse. This is an example of what a simulated environment in Morse looks like, and you can use the command line to send commands to different agents and see what happens within the environment. So the questions we were expecting to answer by the simulation were the following four. Are there any hazards highlighted by Morse which are not detected by Zot? And the other way around, are there any hazards detected by Zot which doesn't look problematic by Morse? Does Zot reports the most hazardous situations or Morse? And which one has less false positive reported cases? False positive being cases that satisfy the formula describing hazards, but in fact are not problematic. For example, contacts between human and robots that are needed by the executing task. So we implemented the orchestrator that fits more into our toolchain and validated it through two case studies, one of which we'll be discussing here now. We have used an industrial manufacturing task as our test case in which a KUKA manipulator arm mounted on a moving platform needs to grab a piece from a given position, move to where a human is standing, and then hand them the grabbed piece. The human is free to move around the workspace while robot is moving, and thus contacts are very much possible. You can see a representation of the layout of the case study, which shows a partial discretization of the work cell into three-dimensional cubic areas, which could be mapped into the simulation environment by creating a correspondence between discrete locations of the formal model, so pink cubes, and Cartesian coordinates within the simulated environment. There are hazardous situations detected by the model checker which are not depicted as such with the simulator, and thus could be perceived as false positives. The figure on the left, for example, shows an example of Morse output where the situation seems to be harmless, but the model checker reported a hazard. We suspect that the problem is due to the discrete definition of the layout in the formal model. Basically, when the robot gripper, so the end effector of the robot, and the human arm are at the same location, the model checker recognizes them as being very close and possibly touching each other. However, the simulator shows that it might not necessarily be the case. This could be the additional precision that 3D simulation could add to the model checking results. The figure on the right, however, is the Morse output for another time instant, where model checker and simulator both detect a hazardous contact between human arm and the gripper of the robot. Remember that the output of Zot is a bunch of Boolean assignments for all the predicates and variables of the model. We had two main observations during the evaluation. The discrete definition of the layout and the time makes the translation of a formal model to a 3D viewpoint not fluent. Movements in formal model are defined as moving from one location to another. And the bigger these locations are, the less smoothly movements will be simulated. For example, in the figure, if the gripper needs to move from location 1, so the pink cube 1, to location 2, which is pink cube 2, below that, the temporal formal model captures this move by assigning a time bound to it. For example, if the gripper is moving from 1 to 2, then it is moving out of 1 while it is still in 1 for 3 time units, And then after that, it will be in location 2. However, the simulator would depict a sudden jump from 1 to 2 after 3 snapshots. This will create a simulated trace of the system, which does not seem very smooth and fluent and natural, basically. So in order to resolve the mentioned problem as future step, we want to inspect what is the best layout discretization scale that provides a trade-off between the size of the model so that we won't face state space explosion and the smoothness of the movement shown by the simulator. Moreover, we have 2 models of human. One mirrors the normative behavior, which is basically following the instructions correctly, and the other one is a formal model of the most frequent human errors while executing industrial tasks. Up to now, we have not included a second one within our experiments with Morse, and we are going to do that and see how the results would be. Finally, we want to try out different simulators such as VREP to see if they could improve the movement issue with different motion controlling commands. Thank you very much for your attention.